Okay, I guess it's 11 o'clock. So I want to get back to the idea of traffic flow. Oh, and before I forget to mention, for those of you that weren't in my previous class, this Monday's class only, this is the only one hopefully this semester, will be asynchronous. Instead of meeting at 11 o'clock, I will prepare a video for you to watch, and you can watch that at your leisure. It'll be the only class, I hope, this whole semester where we won't be meeting synchronously. So remember what we were talking about last time? We had this road. Say one lane of road. And let's say that the speed limit is 60 miles per hour. And we're going to break this down into segments like we did with our heat flow. When you artificially break a continuous thing down into segments, it's called putting a mesh on it. So we're meshing the road. And we did the same thing with our bar when we were talking about heat flow. And let's say we have, segment I here, here's I plus 1, here's I plus 2, here's I minus 1, and so on. And on each segment of the road, let's say each segment is 1 mile. That might be too long to break things into, but we'll say each segment's 1 mile. So these markers are 1 mile apart. And at 60 miles per hour, it's going to take you exactly 1 minute to drive from here to here, 1 minute drive from there to there, and so on. And on each segment of the road, on segment I, we have a density. Of cars, measured in cars per mile. So let's say the density on segment I is denoted D with I in parentheses. So this will be the density of cars on segment I. So if D of I is 30, there are 30 cars on segment I. There are 30 cars per mile on segment I, but since each segment is exactly 1 mile long, D of I also happens to be the number of cars on segment I. If there are 30 cars on segment I, there's 30 cars per mile on segment I because the segment is 1 mile long. So this also happens to equal the number of cars on segment.
Wait,
Yes, Jackson.
so the density of cars on segment I'm sorry, I read that as number of cars total, not number of cars on segment.
This last thing does say the number of cars total on segment I. I mean, since each segment's 1 mile long, the density is equal to the number of cars. I mean, if I have a 1 mile long unit of road and there are 30 cars on it, then the density is 30 cars per mile in that segment. So it's just because I happened to pick each segment to be 1 mile long. If each segment was half a mile long, then the density would be half the number of cars, sorry, the density would be half the number of cars on that segment, right? So it's just that I picked each segment to be 1 mile long, that density and the number, density in terms of cars per mile and the number of cars on that 1 mile segment are exactly the same, just because the number of cars, and just because the length of the segment is exactly 1 mile. Now, past a certain density, we talked about this last time, the speed of the traffic drops. So speed of traffic begins to fall. We knew that speed of traffic falls to maintain a 2-second lead time between cars. So up to a certain point, so if density is along this axis, density D in cars per mile, and velocity is on this axis, so speed is on this axis. Up to a certain point, everybody's going to drive whatever they're going to drive. So we'll just say everybody's a law-abiding person. They'll drive 60 miles per hour. And then after that, to maintain 2 seconds of lead time between you and the car ahead of you, you're going to have basically a reciprocal function. You'll have a function that looks like this. And of course, this will approach the horizontal axis asymptotically. Now, this model is not quite right for a variety of reasons. And we'll talk about that in a second. First of all, and you pointed this out last time, 99.5% of drivers do not drive at the speed limit. That doesn't require too much explanation on my part. Most drive above, a little bit, a lot. A few drive below. What was that? Okay. So, but most don't drive right at the speed limit. The second problem, well, the second problem has to do with, or the other problems have to do with this section over here. For one, your speed's going to start dropping before the car ahead of you is in the 2-second zone ahead of you if you see traffic that is much slower ahead of you. You're not going to wait until you're sort of 2 seconds behind almost stop traffic to start slowing down. That would be stupid because you'd have to skid to a stop, and if you didn't hit the car in front of you, somebody behind you is going to hit you. So instead, you start braking much earlier. Secondly, this can't really be true because we can't keep getting closer and closer to the x-axis because cars can't get arbitrarily close together. I mean, if we measure the car from the front of one car to the front of the next car, the closest they can get together is the length of the car, right? Unless, no, they can't get any closer together than the length of one car. That just can't happen. So this isn't quite right. We're going to use a slightly different model. And it's also going to be easier for us to work with. Instead of using this model, I'm going to use this model. So again, densities here. So density D in cars per mile. And this will be your speed again in miles per hour. And it will start at 60, and it will stay 60 up until we have 30 cars per mile. So up until in a 1 mile segment of road, there are 30 cars. That's going to be about 2 seconds of lead time. At 60 miles per hour, if there are 30 cars per mile, we have about 2 seconds of lead time. Slightly less because of the length of the car, but that's going to not be a huge factor. After that, I'm going to have this drop off linearly. I'm going to have it drop off, and at 60 miles per hour, we're going to say the traffic is at a dead stop. Didn't draw that very well. Now, actually, you need well more than at 60 cars per mile. Yeah. We're going to say the cars are at a dead stop. You can actually have cars much closer together than that before they really reach dead stop. It's going to take probably around twice that in reality, in a real world situation, before the cars are basically not moving. But we'll just stick with 60, just to make our lives very easy. So this function right here, so if S is speed and D is density, speed is a function of density. So let's say S of D. You know, it's weird to see a capital letter inside the parentheses and a small letter outside. This is going to be your speed on segment I in miles per hour at density D. And according to the picture that I've drawn here, we can work out what a formula for S of D. S of D equals one of those piecewise defined functions that we all know and love from like calculus. So S of D equals, it's just 60 as long as D is between 0 cars per mile and 30 cars per mile. And then it's this line. It's going to be, so this line, if you see where it hits the vertical axis, it's at 60. And if you figure out its slope, it goes over 30 and down 60, so it's -2. For D, draw this a little bit bigger. For D between 30 and 60, and then we'll say traffic's at a dead stop after that. So between 0 and 30, everybody's going to be driving at 60 miles per hour. Remember, the 0 and the 30, that's cars per mile, cars per mile. So an empty highway, 30 cars per mile. Between 30 and 60 cars per mile, the speed just drops linearly, and then everybody's at a dead stop after 60 cars per mile. You've probably all been stuck in traffic, which was essentially not moving. I have. I used to get stuck on the Cross Bronx Expressway all the time. And that gives us a picture that looks like this. And now, what we want to do is come up with an initial traffic density profile. Determine what happens over time. How does traffic density evolve over time? So what we're going to do is we are going to build propagation equations. So we want to build propagation equations, design propagation equations, maybe that's a better word. Which will tell us the traffic density and hence the speed. In all the segments. At time t plus 1, based on traffic density in all segments at time t. So we already know what our length of mesh is in terms of distance. We broke this up into 1 mile segments. I have to decide how to break up time into segments. I'm just going to arbitrarily, this was an arbitrary decision. I broke this up into 1 mile segments. I figured that would be nice and easy. I'm going to make another arbitrary decision and break up time into 1 minute segments. So advance in 1 minute segments. Take a look at 1 segment. So here's segment I, here's segment I minus 1, and here's segment I plus 1 of road. So between time t and t plus 1, the density in segment I change in the density in segment I. I don't know if you're used to seeing this before a variable. It just means it's delta. It means change in. The change in density in segment I. So in other words, this will be, so now density will have two variables. It will have the position we're in segment I. So the change in the density in segment I, so di t plus 1 minus dit. So how much has the density in segment I changed between time t and t plus 1? Remember, since I broke this up into 1 mile intervals, the density in terms of cars per mile is the same as the number of cars in that segment. So the change in density is going to be equal to the number of cars which enter segment I between time t and t plus 1 minus the number of cars that leave. Between, oh, that leave. Oh, number of cars that leave segment I between time t and t plus 1. So the total number of change of cars between time t and time t plus 1 in segment I is going to be the number of cars that enter minus the number of cars that leave. If more cars are entering that segment than leaving, the number of cars in that segment is going to go up, and the density is going to go up. If the number of cars leaving is higher than the number of cars entering, then the density is going to drop. Does this make sense? So, in other words, to figure out what dit plus 1 minus dit equals, we have to figure out how many cars are entering minus how many cars are leaving. So let's figure out how many cars are entering.
If all of them are moving at 60 miles per hour, then the number entering would just equal the number in the previous
Right.
cell.
Yeah, if everything's moving at 60 miles per hour, then it's just going to be exactly what you just said, the number in the previous cell, because all those cars are going to enter.
Okay.
So how many cars enter? So again, we're going to be looking at the previous cell, just like you said. It's going to be, let's see. This is going to be the number of cars in the previous cell. In other words, the density of cars in the previous cell, because the number of cars in a cell is the same as its density, because each cell is 1 mile long. Number of cars in cell I minus 1 at time t times the speed in terms of miles per minute. So speed of cars in cell minus 1 at time t. That's in miles per hour, but I want this in miles per minute, so I have to divide by 60. So at 60 miles per hour.
What is x?
Oh, no, that's times.
Oh.
Here, let me change that to a dot. So at 60 miles per hour, all the cars in this 1 mile stretch are going to move into this 1 mile stretch. At 30 miles per hour, half of them will. At 20 miles per hour, a third of them will, and so on. So let's write this a little bit shorter. The number of cars in cell I minus 1 at time t, that's just the same as the density of cars in cell I minus 1 at time t. So that's d I t, sorry, I minus 1 t times the speed of the cars in cell I minus 1 at time t. So that's times the speed of d I t divided by 60. And the reason we're dividing by 60 is because we're going from miles per hour to miles per minute. So how many cars leave? You can see for how many cars enter, that all depends on what was going on in the previous cell. For how many cars leave, that all depends on what's going on in the current cell. So how many cars leave? It's the number of cars in cell, that same cell at time t, times the speed of cars in cell I at time t divided by 60. Again, divided by 60 because instead of miles per hour, you're talking about miles per minute. You go 1/60th the number of miles per minute is miles per hour. Yes, Wayne.
In the propagation equation you just wrote, when you do multiply times the speed of density, is that supposed to be I minus 1?
It is supposed to be I minus 1.
Okay, I was just making sure.
Thank you very much. Absolutely. Yes. My bad. So the speed of cars in cell I at time t. That's in miles per hour in our original, but we're going to divide by 60 to change it to miles per minute. because we're measuring our times in minute increments, not in hour increments. And so this equals DIT times the speed of, if you have density, that density, DIT all over 60. Again, the divided by 60, just to convert from miles per hour to miles per minute. Okay, so let's put this and this and this together. So we said, if you don't mind if I erase what's up here. So DIT plus 1, the density in cell I at time t plus 1 minus the density in cell I at time t equals the number of cars that enter the segment, which is this, minus this, the number of cars entering minus the number of cars leaving. So let me, wish I had more space on the blackboard. So the number of cars leaving is the density in segment I at time t times S of D I T divided by 60. So if that looks horrible to you, let's stop and just look at it carefully. What's on the left-hand side of the equal sign is by how much the density of traffic in cell I changes between time t and t plus 1. So the delta, the change in the number of cars, basically, since density is equal to the number of cars, since each segment is 1 mile long. So it's the change in number of cars in cell I between time t and t plus 1 is equal to the number of cars entering minus the number of cars leaving. That should hopefully make intuitive sense. Does that make sense? The change in number of cars is the number of cars entering minus the number of cars leaving? Awesome. And so it's a long formula, but it should be intuitive. Also notice that of all the terms here, the only one that involves time t plus 1 is this one. Everything else involves time t. We're trying to get propagation equations. So we're trying to solve for density at time t plus 1 in terms of the densities at time t. So let's just keep this on the left-hand side and move everything else on the right-hand side, which really only means moving this one term over. DIT plus 1 equals, I'm just going to add this to both sides. DI minus 1t times S of DI minus 1t over 60 minus DIT T times S and D I E over 60 plus, when I add this to both sides, D I T. And we are practically finished. We practically have our propagation equation right there. We basically do. The only thing we need to remind ourselves is what that S of DIT was. So recall, S of D was 60 if S is, sorry, if D is between 0 and 30, it was equal to, what, 120 minus 2D if D is between 30 and 60, and it was equal to 0 if D is greater than 60. In other words, you already have this in your notes. So this is your speed axis. This is your in terms of miles per hour. And here is your density axis in terms of cars per mile. Basically cars. One of our segments is 1 mile long. And it's 60 up until the time you hit 30. And it drops off linearly to 60 and then is along the x-axis ever after, or on the d-axis ever after. So we have our propagation equation now. This is basically ready to go into an Excel spreadsheet. All we need now are additional conditions, and we can make them up any way we want. So now we need initial conditions. So we'll need density in segment 1 at time 0, and density in segment 2 at time 0, all the way up to however many segments we have. Density in time in segment n at time 0. So we'll specify these in cars per mile. We will plug in our initial conditions. We will plug in our propagation equations and watch what happens over time. 10 minutes. So first of all, one thing that you might run into trouble with when you're using Excel to do this problem is this function that we have right here. How many of you have used conditionals before in Excel? Like, if this value is between here and here, then this equals that. No, you haven't. Has anybody used conditionals before in Excel? No. Some of you, I think, have, if you were in my, what's it called, data science class, when was that? Last semester, I guess. Seems longer. And so you may have used them before and just have forgotten. But Excel does have conditionals. Let me bring up Excel and share my screen. So let's see. Excel is very helpful. Usually, if you have a question, you could just go ahead and ask it. Let's say. So let's go here. I don't want to do that. So let me go down here and okay. So let's say if B2 is greater than B2 is greater than 5, then no, let's say if B2 is greater than 30, then this will be equal to 60 minus B2. Oops, 60 minus B2, and if it's not greater than 30, it will be 60 minus B2. I want 120 minus 2B2. Sorry, I have trouble typing. B2. Oh. And it's going to be 60 otherwise. And so you can see that I have this if statement here. So this is, if I have like if I put 20, which is less than 30, I have 60 here. If I have 30, I'm still going to have 60 here. But if I have 40, it's going to start dropping. You can see what I have. What I've put in here is the first part of that piecewise defined function. Now it doesn't go down to 0. So let's see if we can do a multiple if here. B2 is greater than 30, then 120 minus 2B2, otherwise 60. So what do we call it? Is it case?
Why 120?
Oh, remember remember that if that step equation that I gave you that sort of went across and then went down and then went over, that it was 60, it was constant 60 for a while, and then it was 120 minus 2x in that part where it went downhill.
I thought it was 60 minus 2x.
It was 60 minus 2x?
Yeah.
I wrote 60
because it
minus
was
2x?
like decreasing.
Yeah, I know, but if you, so hold on, let me stop sharing my screen for a second. I wrote 60 minus 2x?
Yes.
Oh, Well, that was a mistake on my part. Hang on for just a second. Let me stop screen sharing. So what I meant to write is 120 minus 2, like 120 minus 2d for this part right here, because it's decreasing, but if you look to see where this thing crosses the vertical axis, it actually crosses, like this is the vertical intercept, right? That's at 120. That way, when you get to 30, it's down at height 60 already. To make this a continuous function, this can't be 60 minus 2d, because if you plugged in 30, then you'd be at height 0. We'd jump from here down to height 0. You want it to still be at height 30 here, at height 60 then. So it should be 120 minus 2d. That way, when you plug in 30, it's 120 minus 2 times 30. You're at height 60 still. And if you plug in 60, you have 120 minus 2 times 60. You're at height 0. So that little piece there is 120 minus 2d. And this, of course, is just a constant 60. This is a constant 0. That explains the first and the third line. But if I wrote 60 minus 2d at some point, I really didn't mean to. I meant to write 120 minus 2d. So what we just put in there with that if statement is this much of the curve, but it goes down. So now we have to figure out how to get it to go over again. So I need a double conditional in there. But I only have 3 minutes to figure this out. Anyway, I think what I'll do is I'll pick this up. Maybe I'll put this in the video that I prepare for Monday, and we'll see if we can finish this off. And I'll have you put this into Excel and see what happens over time. It's really interesting, and it models behavior that you have probably seen before while you were on a road, whether or not you were the one driving or not. And I'm not gonna tell you what it is right now. I'm gonna wait for you to just sort of discover it yourself, because it's really interesting. Anyway, are there any questions? Is everybody okay so far in terms of this propagation equation we have right here? Okay, that's the super important part. And then we'll just figure out how to get this into Excel. That's what I'll put in the video. And that's really the last thing you need to know. So we'll figure out how to put that into Excel, and then we'll run it and see what happens. All right, well, that's it. Have a good weekend. I probably won't see you on Monday, but hopefully you'll see me and have fun with this assignment. And yeah, there we go.
I don't know how people leave so fast. Like by the time I've scrolled my little thing to the X, everybody's gone. Like,
they probably have their finger hovering right over.
It always amazes me. Like by the time I move my mouse there, everybody's already left. But I also had a question.
Yes.
In our last math senior sim, Dr.
Yes.
Juan told us we just email you with who we prefer as our advisors.
Yep.
Okay, sounds good.
Yeah,
right,
so
you have
if
a
you
good
could do that
weekend.
today, I'd appreciate it, because over the weekend I want to get you matched up, and so I have to talk to Dr. Juan and Dr. Penn and get everybody paired off. And
Okay.
You might not get your first choice, but hopefully you'll get your first or your second.
Okay. All right. You have a good weekend.
You too.